Hello, everyone, to this webinar. I am so excited to be talking to you about my all-time favorite topics. So I've been covering data and analytics for many, many years now as an analyst, first at Gartner and now as an independent working for myself in a company called SanjMo. And then I decided I moved into the space of data mesh and data products last year because I find that data products is such a transformative new way that, and we'll talk more about why data products are a breath of fresh air. But then something really strange happened this year when suddenly through my roof, this rocket landed in front of me, and it's called generative AI or LLMs. Being one of them. So all of a sudden, we had to make this hard pivot. And typically, most of my webinars, my writings talk about these two topics very separately. Data products is one, generative AI is another one. Today, for the first time, we're bringing it all together because it doesn't make sense for us to have these as two separate spaces. So with that, I am delighted to be on this webinar today. My name, as you know, is Sanjeev Mohan, and I know many of you and I'm acquainted, but as I said, I now run my own advisory company called SanjMo. Stavros is with us today. And Stavros, can you please introduce yourself?
Thank you, Sanjeev. Thank you also for co-hosting this webinar with me. Hi, everyone. I'm Stavros, founder and CEO of TileDB. We're going to have the time to cover a lot of important topics with Sanjeev. And at the very end, I'm going to tell you how TileDB fits into the picture. So I'm very excited about this and looking forward to what comes next.
Excellent. So let's get started. By the way, we have so much material to cover. We are going to go fast, but as Mike said, please ask your question, post it in Q&A. Happy to stop and answer your questions. We are covering a lot of new ground. So what is all this fuss about? Why is everyone now so deeply entrenched into all this discussion? It is because at the end of the day, what do organizations want? They want meaningful insights, and they want it at the speed at which they're making these decisions. The problem is that they have a lot of data, and this amount of data they have to deal with is just increasing all the time. So the whole topic is, how do I get meaningful information, insights? What are my challenges? So the first challenge is that not everybody understands the data at the level it needs to be understood. For example, how many years we have spent with data engineers like myself, having to muck around with, let's say, clinical data, and trying to join tables and aggregate them. But the experts who understand the data are sitting somewhere else. In domains, so we don't have adequate understanding of our data. On top of that, we are living in this modern data stack where we are segmenting and micro-segmenting our data infrastructure by having categories of products. And now we have either not enough systems to manage and analyze our data, or we've pivoted towards having way too many systems, which means that we, again, have a people problem. So we have a problem with understanding the data. We have a problem with understanding the systems, and bringing these together is such a challenge that what it leads to is you need a lot of talent, which we know is not easy to find, and you need a lot of investment. One of the biggest questions I get in the year of 2023 is, what is the value of all of this investment in data? It's an area that some people call FinOps, but optimizing for cost is one of the biggest requirements in the current economic situation that we are in. So what does that lead us to? Status quo. Let's just keep using our current data warehouses, because we understand data warehouses and we've been using them for past few decades. Anything that's not structured or tabular, we call it unstructured. for which then now we need to rely on specialized databases. This whole thing started in early 2000 when the whole NoSQL came into existence. With NoSQL, we had a database for a specific use case. Key value stores for fast lookups, document databases for maintaining catalogs, graph databases for recommendations, wide column databases for sparse data lookup, and then of course relational databases for for high consistency transactions. But having too many specialized databases means that now I've got too many formats, too many tools, which means my cost is going up. I need more talent. So instead of trying to solve my problems, now it ended up that I have a data silo in one place using a certain technology with a certain team. So we've got now too many data silos, disconnected teams. In fact, as we get into the space of AI, the whole notion of garbage in, garbage out is becoming right center for this problem, because if we don't have a single source of truth, or at least we know where to find the right data, how in the world are we going to do any predictions on it? To get the single source of truth, now we have embarked upon very complicated data wrangling processes. We are trying to get data from multiple different places, trying to understand where they are, what they mean, join them, wrangle them into some sort of an analytical store, which means we've got high cost, high complexity, high number of talent that is needed. And a lot of this manual work means now we need to invest in yet another set of automation tools. In other words, once again, we are slowing down our approach and our way to get data insights. But fear not, there is a solution. It's a data mesh. So what is a data mesh? So data mesh came out in about 2019 or so with a set of principles. The whole idea was that let's become more domain oriented. Basically, we are borrowing some principles that we have learned very effectively from software engineering. So amongst these four principles, domain oriented, data as a product, self-service data infrastructure, and governance, federated computational governance. These are the four underlying principles. The most exciting one is data products. So why do I say that? It's because data mesh is a concept. And the problem with concepts is that there is not enough guidance. The second problem with data mesh is that not very many people understand what it is. But data product is a consumable piece. What is a data product? So we will see that in just a second. What data mesh is trying to do is it's saying that our entire approach, where the business users as a data engineering team to provide some information. Stavros actually, as when we get to the next slide, he has some really great practical examples of what his clients are asking. The problem is that the data engineers will spend a lot of time trying to get this information. Data mesh says, no, why don't we remove this bottleneck, send the expertise to the data sources, to the teams that understand the data. So data mesh is actually an organizational cultural shift, where we are using the domain experts and making them accountable for the quality of data, for the insights that are delivered. Those insights are delivered as a data product. A data product is a self-contained piece that contains the data, contains the logic that goes around it, and the access method, which is APIs. Plus, it has all of its infrastructure, and it has SLAs. These SLAs are what's the reliability that I can expect, what's the uptime, how often is my data refreshed. All that is contained so that the data consumer knows exactly what he or she is getting. However, the data consumer may not be a business analyst, may even be a downstream system. but there is a clear understanding of what are the KPIs, the SLAs, and that is actually something that we're not talking about in this presentation, but it is something that we are encoding in a machine readable form that we call a data contract. But that is now getting deeper into data products. These data products, what they do, the best part is they increase a release cycle. I no longer have to say, I'm a bank, every 6 months, I have a new product. I can have a release cycle every 3 weeks if I want, using the data products approach. But how do I discover the data products? That is why catalogs become really important, because not only can I discover, I can govern, but there's another huge advantage. I can measure which data products usage has gone up. I can discover who else in my team is using that data product. So I get both the metrics and I find out who is my community, my data tribe, if I may. And if I can measure the usage of these data products, then I can increase my productivity. So the whole organization benefits. But all this sounds great. It's like, okay, so what's the problem? Let's just do it. But there are certain problems. The very first problem, as I have said it before, data mesh is a concept. There is no how-to guide. In fact, a lot of organizations are now successfully doing data mesh, except they may do it very differently because there is no reference architecture. And in that case, anyone can say, I built a data mesh. So sometimes we are a bit skeptical because there might be a bit of data mesh washing going on in the industry, if you may. Second problem is when you move the accountability to the domains, you have to remember, if a domain was so used to always relying on a centralized data engineering team, all of a sudden they are now responsible for building these data infrastructures, and they may end up building silos. So we went out to remove the silos, and we've added more silos, we've added more complexity to our process. And data business analysts are not software engineers. They may not even know what are the best practices in version control, release management, automation, CI/CD. So now we have multiplied that complexity. As a result, no one still understands the value of data products, and we unfortunately end up from data mesh being a solution to becoming another hype. So talking about hypes, let's pivot. Now let's move to yet another hype, and this hype is now called generative AI. So who better to talk about generative AI than Stavros, because he's been solving and trying to solve and get over this space for many years with some practical examples. So Stavros, I'm going to hand it over to you and have you talk about generative AI. Please carry on. So I'm going to stop sharing my screen so you can take it over from here.
Thank you, Sanjeev. All right. So just to summarize, organizations want to get insights. They have a lot of data, very diverse, a lot of different technologies that they bring into the organization to solve this, a lot of data engineers to harness those technologies. And data mesh is a nice concept around putting a little bit more sanity on what the organization has to deal with, because every organization has to deal with a lot. And all of a sudden, as Sanjeev said, generative AI happens. So let's drill down a little bit in order to understand what this is and how it ties into everything else that has been mentioned. So generative AI revolves around large language models, huge advancement there. This is not a course on LLMs. I can answer questions and everything, but I'll try to considerately oversimplify to convey the main message. Those are some machine learning models that are extremely powerful. The bottom line is that they can provide answers to questions in natural language. So you ask something in natural language, you get something back in natural language. So you can interact very naturally with those. People like to think of LLMs as some magical boxes with all the answers because they've seen all of those posts on LinkedIn and Twitter with really beautiful things that the LLMs can do. And of course, it's beautiful because they don't have to learn another language, particular API. They don't need to become data engineers to get answers to those questions. They may not be data engineers. So they tend to think those LLMs are magical. And here's an ideal scenario that several of our customers have brought up, but a lot of other people are thinking about. So I'll use an existing LLM from OpenAI. Those, mind you, and I'm going to explain more later, they're extremely expensive to create, both in terms of tech, but also in terms of computational power to create them. So I'm just going to use something that exists already. Probably it's going to be much less expensive to pay some licenses for that. I'm going to ask it any complex question I have in mind about my organization, not about Wikipedia, about my data, my personal data that I have in the organization, my sensitive data, and I want to do it in natural language. I don't want to think about databases and all of that stuff at all. I don't even need to interact with data engineers. For example, we're working with some doctors, and doctors are telling us, what kind of queries to run and all of that stuff because they're doctors, they're not data engineers, and ideally they would want to ask questions in natural language. Who out of my patients is prone to cancer in the next 5 years, and everything magically should happen in the background without any SQL queries or any other API queries. The problem that a lot of people, you're going to be surprised how many people oversee this, is that the LLMs have absolutely zero idea about my data. Zero. It has not been trained on my data. So no matter how smart it is, it doesn't know anything about my organization's data. So just thinking that you're going to use an LLM and that's it is not cutting it. So drilling a little bit further, because don't fret about it. There are solutions. I'll tell you what solutions exist. Let's drill a little bit further. What is an LLM? So, a lot of you guys that may not even be in the area should understand that this is a machine learning model. It's all about machine learning. It's in fact a neural network. It's very complicated. There is a lot of sophistication in there. It takes input text, but also other data modalities. It may take images, it may take audio. It's smart. So it can take as input something enhanced, and it produces text that is understood by you, like in natural language, and also it can provide other modalities as well, right? It can output code, it can output an AI generated video. Again, it's smart. But the LLM is trained on certain data, right? And this data is not yours. This is data that OpenAI chose to train this on over the past few years. Some were with human guidance, some others were not. Again, a lot of sophistication, a lot of work into this. These are very involved domains. But the bottom line is that the LLM knows nothing about your data. So the LLMs, in other words, are completely irrelevant to your organization unless you adapt them. ChatGPT knows nothing about your DNA sequences and your geospatial data and your time series for fraud detection. It knows nothing about all of that stuff. All right, so what do? You have three options. Option number one, retrain the LLM with your data completely from scratch. This is also known as make NVIDIA very, very rich and yourself very poor. It takes millions of dollars, literally, to build those models from scratch. So let's say that this is out of the question because it's insane. The second one is another option where you can fine-tune an existing large language model with your data. That's not as bad as the first. So you're going to still make NVIDIA quite rich or somewhat rich and yourself somewhat poor, still going to cost you a lot of money, but it's simpler. Effectively, think of the LLM as a neural network with multiple layers, like as in a pipeline. And the first layers are very expensive to train, and those are trained. The latter layers are a little bit easier to train, more inexpensive. So you focus only on those ones, adding your data, and then you have a fine-tuned LLM. A very valid approach, but still expensive. You need machine learning experts that understand the data. And you use this when you really need a fine-tuned model for what you do, like really, really fine-tuned model. The third approach that a lot of people are going for is that you can customize an existing LLM. You're not touching it, you're not retraining it, but there are libraries that add something called tools and agents. It's a beautiful, like LangChain, for example. And this allows you to, as I'm going to explain the next slide, like customize it. And this is beautiful because you may make OpenAI and Google a little bit rich, but in a very cost-effective for you way. so this is very, very valuable. So I'm going to focus on the third approach because it is very relevant to what we're saying about databases and data products and data meshes. Everything is going to eventually make sense, right? But for now, I'm going to tell you how you customize generative AI with the data of your organization. All right, so how do we do this? So instead of, I don't know who has used ChatGPT before, but it's very simple. It has a prompt. You just add the question or something, and then you submit the question and you get an answer. So instead of doing that, you can augment the prompt with context. This is what the LLMs are extremely good at. You can ask a question, you can provide additional context, additional data, and then you can instruct the LLM to respond to your question with respect to the ancillary data that you're providing. That's very powerful. So the context, when we talk about context, we really mean relevant data, data that is relevant to this query, and also that it comes from your databases. It's not just any data, it's data that you're already storing in databases that you have. And this, again, can be achieved with these tools and agents and libraries like LangChain. So visually, this is how this looks like. You have a prompt, but you make it context aware. You ask your question, but you add some data, and the agents and the tools in LangChain will help you do that in a more automated way. So this is why LangChain is beautiful. And this gets into the LLM, and now your answer is very relevant to your data. And this is powerful. And this is what a lot of people are doing. But what are the persisting challenges? You still need a stack to manage this multimodal data. This is key. In addition, of course, to all the traditional analytics that we have. So let me repeat this because this is extremely important. LLMs are not replacing databases whatsoever. You are actually adding complexity. You're not removing, you're removing complexity from your users, but please don't be mistaken. You are not removing complexity from your organization. Now, in addition to all the databases you need to provide these tools to these agents in these LLM, LangChain libraries, you also need to, first, you need to build those tools, agents. That is not trivial. I mean, LangChain is a great product, but there is, sophistication and expertise that you need. But also you're adding one more layer, which has not been on the surface up until now, which is called semantic or similarity search. The reason is that relevant data in a lot of the queries cannot just be retrieved by a SQL query. It could be something fuzzier. I have an image, show me the similar images to this image, to this X-ray, to this CAT scan. And that cannot be achieved by just a SQL query. You need something else. So far, we can build, this is the takeaway so far, and I'm going to take a pause in case Sanjeev or anybody else has a question. But so far, yeah.
I mentioned you might want to share some practical example of what people want from LLM, and is there one of your client examples you can?
Yeah, absolutely. As I mentioned, right, we're working with doctors. Doctors are very smart, but they're not going to spend time learning SQL or the TileDB APIs or another API.
Yeah.
They're trying to find likelihood for a genetic disease for an infant, for a newborn baby. And they need to search in their database for similar patterns. And in order to do this, they need to query those databases. And even if you give them and we're going to talk about this, some low code or no code environments, still are going to say, oh, okay, but I need to adapt my search now because that's not exactly what I'm looking for. And I need to improvise a little bit. Well, this improvisation is better captured by, a prompt where they can write anything they want. They want to say, search this, and then do this, and then combine this with with an encyclopedia repo about genetic diseases. That's what they want. They don't want to do it manually. They still require the stack. They need a database for DNA sequences. They need a database for phenotypes. They need a database for X-rays and other ancillary data. They need those, but they don't want to go to every single database, do the queries, wrangle them, join them, iterate over them, and so on and so forth. They want automation. So who automates that? An LLM. But the LLM has to be augmented, customized with their data, not only with the repositories in the biological and medical encyclopedias on the internet that the LLM was trained on. They need to input their data. And this is exactly what this customization is doing. And you can think the same thing for IoT and 5G applications for telecoms. We have a very similar use case there with a telecom company. They have a lot of images. They want similarity, and they want to be able to do it in a prompt because the business experts just don't speak SQL, or they don't speak another API that you're giving them. So that's why this is very, very powerful. The problem, and this is exactly what the rest of the presentation is going to focus on, is that those LLMs still are not those magical boxes. It's just an API. We just add an API for our no-code business analysts and scientists. And this API needs to interface with all the databases that you have, plus an extra one, because that extra one became very relevant for this kind of queries. The users want to find similar stuff, similar PDF, similar images, similar audio, similar video, and this similarity cannot be expressed with an exact SQL query or another API query. You need to do something called semantic search or similarity search, which I'm going to focus on in the next slides. All right, so moving on. So what is similarity search? Well, as I mentioned, similarity between certain objects, like video, audio, imaging, and others, just cannot be expressed as an exact database query. Think of an image that has a cat at the bottom left, and another image that has a cat at the bottom right. You cannot just do a pixel by pixel comparison and say those are dissimilar because the cat is at the bottom left and in the other image the cat is in the bottom right. You just cannot do that. Like, these are similar, maybe not identical, but they're still similar. They both have cats, and those are dissimilar to images that have dogs, right? So you need to be able to express the similarity in a smarter way. You cannot do just an exact database query for that, a tabular query. It's not going to work. So the idea, and this is a very deep domain. This domain has existed for decades. Some people think about similarity search and other hypes that came up like a couple of years ago, and they think that they're new. This has been around for decades. All right, so the idea here is to take an object, like an image, and convert it into something mathematical, into a vector. It's called a vector embedding. It's a list of numbers. So we go from images of cats to lists of numbers. And think of those lists of numbers as a very intelligent compression of the features of those images. And the same is true for audio, for video, for PDFs, and so on and so forth. It's a compression mechanism, a very meaningful compression mechanism of those features. So now, if you want to compare two objects, instead of comparing the raw objects, you compare the vectors, because there is a mathematical relationship between them. And all you need to compute is a so-called distance. And typical distance, this is a metric. This is a mathematical formula that you apply on the two vectors. And usually it's Euclidean, it's inner product, and there are many, many more. But that's it. So we go from a fundamentally difficult problem to something very well defined. like similarity between lists of numbers. Excellent. So what's the problem here? The problem is that if you want to compute this distance across billions of those vectors, because you may have, it really depends, and we're going to get back to this, but if you have an organization where you have billions of images or billions of audio or billions of whatever other, objects that you want to search on, this computation, this query is not easy. You need some kind of a specialized software for this or specialized functionality. And this is exactly after all this entire timeline that we built over the past 30 minutes, it brings us to the new hype that complements generative AI, which is the rise of vector databases. So what do those vector databases do? So like any other, like with other data types, like tables and images and others, people want storage, fast search, and of course, governance. And therefore, they use some kind of a piece of software, let's call it a DB for now, a database, that does the following. It manages those vectors. It handles updates, governance, time traveling, logging, things that the database would do for your tables. The same thing should be done for the vectors. It creates indexes, extremely important. It doesn't scan everything in the database. It creates intelligent indexes, and it searches for similarity faster. And by the way, those are also well known, predominantly approximate. You're not going to get the exact answer, but that's okay. But those are well known. They have been in research for, again, decades. It's not a new problem, but now it became relevant. So you have a couple of options when it comes to vector databases. The first one is that you can use a library, not a database. You can use something like Vice. It's a library. It allows you to store vectors and do some similarity search. And for the majority of the use cases, probably you're covered. The DB is an overkill. The second thing that you can do is that you can use a specialized database like Pinecone and Milvus, and you saw all this craziness out there in the past couple of months, which provides more like hosting everything in main memory, clusters, SLAs on how fast everything goes and all of that stuff. Or, which also is taking off as we speak, you can use just any mainstream database like tabular or non-tabular, and just wait for them to add the vector search functionality, which a lot have already built. Postgres, Redis, Rockset, they have already built this vector search functionality. Again, these are well-known approaches. It's not that hard to augment an existing database with this functionality. So they've done it. And you can just continue using those databases with this functionality. And admittedly, you can argue here that some databases may be faster than others, different scalability, certainly, but always scrutinize. Start with the basic and see whether you need something. Maybe you don't need a specialized database. Maybe you don't even need a database. You need a library. So this is why you see this craziness around vector DBs. And by the way, vector databases are not only useful for generative AI. It's useful regardless. If you have, for example, recommendation systems, you go on Amazon, you look for a product and Amazon, presents other relevant products. Well, it might be using, some kind of similarity search underneath. So it's not just for generative AI, okay? There is good functionality there and good applicability for other use cases as well. All right, summarizing, what are the challenges still persisting? Because, okay, we built the whole timeline. We have data mesh, we have customized LLMs, we even have vector databases. All right, we solved the problem. Well, congratulations, your stack just became much more complicated than before. Remember, 5 decades ago, you just had Oracle or IBM or Microsoft, that was it. And now you have 1,000 systems. Your data engineering team just exploded. Now you need people that understand LangChain and machine learning. They can build those customizations and all of that stuff. And also the data noise and confusion just became louder. Before you had all those specialized databases. Now you have Vector DBs, you have LLMs. And if you ask any CDO or CIO, you're going to sense the confusion. Like, what do we choose? How do we build this? And then we have data mesh and all of that stuff. So it just became much, much harder to tame all those technologies. The technologies are great, but it's hard to tame. And as we have been saying for many years at TileDB, that's just a, it's the cherry on the cake. This last LLM and Vector DB hype. This is not sustainable. Like, you need to be able to build some kind of infrastructure with basic components that can extend in the future, that is future-proof. You cannot keep adding vendors and software and data engineers and machine learning experts to your organization. You just can't. It's unsustainable. It's gonna break. And this is where TileDB comes into the picture. But before that, the hypes are all the same. It's the same with data mesh, the same with crypto, the same with Vector DBs, the same with generative AI. What usually happens is you see this and you get, crazy about the fundings and valuations. You're hearing some crazy numbers. Don't worry about that. Some are justified. For example, in the LLM space, if you're trying to take on OpenAI or Google, and you're pitching a new LLM, which is remarkably different and more powerful than ChatGPT and Bard, you need tens of millions of dollars just on training. So this money, these valuations, and this funding is justified. Like, you need a lot of money to do this. It's just difficult to compete with those guys because those guys know what they're doing. However, if you're just customizing existing LLMs, then you don't have a lot of defensible IP. This can be done by the engineers internally. If you build think about it like this. If you build a company in a month, probably somebody else can build the same company in a month. Like, this is what happens in hypes. Like, there are thousands of companies out there, thousands of solutions, but if they came up in a month, somebody else can build it in a month. So there is very little defensible IP around hypes. And in the Vector DB space, you need to ask yourself, maybe it's an overkill. How many, for example, I was asking a big institute that wanted to use vector search and similarity and everything. They had some serious data. And I was asking them, how many queries are you going to ask per second? Because these are the kind of SLAs a vector database is going to try to sell you on. And their answer was one per week, not queries per second, one per week. It's needed, but is it really needed at this kind of, SLA structure that you're selling? The 99.9% is going to be no. And as I said, a lot of orgs just don't have that much data or frequent queries for this. They need it. They need to be able to find a similar image. Don't get me wrong. But how many images are they going to have? 1 billion? I find it unlikely. At least the ones that we're interacting with, they don't need 1 billion. And also, let's not forget good old filtering. And this is something that eludes a lot of people. So those images, a lot of times, come with labels. And sometimes all you need is just a label query. It's like a SQL query. And that's it. You go from 3 billion images down to 10,000. And then a sequential scan is fine. So always think about the easy solution before you jump onto something insane. And existing libraries and mainstream DBs, again, Postgres and all of that stuff, should be good enough. It might not be, right? If you're dealing with millions and billions of vectors, probably those guys are going to crash. It's because they were not architected from scratch for this, so it might be problematic. But ask yourselves first, can I do this with that functionality? And also, history has taught us, let's always look into the history. Well, we have seen in-memory databases before, right? For very specific niche applications, you need an in-memory database. For the vast majority of the use cases, you need just data stored on S3, managed by a database, like a data lake. So you need to think about, like, what if I had all my vectors on S3 and I had a very acceptable latency and queries per second that I don't need, an in-memory database for. And also, please remember, Similarity Search is not new, right? Like, always scrutinize the vendors. Like, what's new? Like, Similarity Search, I can count at least 50 papers I have read, like when I was a PhD student a number of years before. So, these techniques have existed for a lot of time. And also, always, I'm going to mention this later, always go to the data experts, to the database experts. Vector DB functionality is easy to build by people that are building databases. It took us 1 month. Postgres, Redis, and others took them less because they've had more resources. It took them less. So always ask yourselves, what is the IP? What is the different thing? Why do I need it? And this is just the cherry on the cake. There is a deeper problem in the domain that we have been talking about for the past 6 years at TileDB. The biggest problem, again, Vector DBs is yet another flavor of specialized databases like time series, key value, graph, and so on and so forth. So very few people take a foundational approach to building something universal, to fixing the relational database instead of building different databases. Why are we building all those different databases and we don't go back to fix what is not working for the new data requirements? And if you build something universal, obviously it's going to be future-proof. You're not going to need to extend your infrastructure again and again and again. You will have just one product that extends itself. But what are the reasons? First, it's too hard. It's so much simpler to focus on building indexes for vector search. It's so much easier to focus on a very specific aspect of time series data, for example, in queries. So obviously, like, who is crazy enough to start building something like this? The second is that you need a ton of funding for this. Databases require funding anyway, but building something that captures so many use cases is absolutely ridiculous. And also, you know, it's very difficult to get funded when you have such audacious visions. Usually, it takes a long time, and this contradicts the interests of both founders and VCs that want to get rich faster. It is the reality, but truly, this is the problem. This is the problem with all the hypes. And also, please remember, cloud vendors, business analysts, and everything, since the past, not now, they have primed the market to believe they need specialized solutions. Like, one size does not fit all and all of this. But let's revisit that, you know, that saying. Is that really true? Can't I do everything with one database that just happens not to be relational? Relational databases cannot do that. I promise you that. But maybe there is a different type of a database that can. So this is what's happening in the domain, and this is exactly where TileDB fits in the picture. Taking another pause here, either for a question or a remark from Sanjeev or somebody else.
This is good. In fact, somebody just commented, it's very refreshing to see that you can use data lake for doing vector search. Any thoughts on that?
You're in for a treat. Stay on the webinar. Okay. You're in for a treat. All right. Okay. Continuing, what is TileDB? Why the heck are we talking about TileDB here with LLMs and all of that stuff? This is the first time, by the way, we're talking about LLMs and TileDB together. But you know, since day one, we have been coining TileDB as universal. So there is a reason why we are extremely relevant here, and everything again is going to tie in perfectly. And this is something I started when I was at Intel Labs and MIT several years ago. It was a research project, and then eventually we spun it out of MIT and we created the company. So in a nutshell, TileDB is a multimodal database, and its fundamental data structure is multidimensional arrays. Multimodal because it can capture pretty much anything you have in mind. So the value proposition is that it can efficiently manage everything. And we can go back and forth and debate as much as you want, but we can also choose a couple of examples and we can tell you why. There is a reason, there is a fundamental reason why we can capture this. With a single solution, we're not building an aggregate of solutions. It's a single solution, one. And I'll tell you how it happens in a bit. And it is based on multidimensional arrays because this data structure is extremely powerful. I have a separate slide about this, and you're going to understand why it is so powerful. But the second value proposition is that if there is one database that can do the tables for analytics, the imaging, the video, the genomics, the embeddings for Similarity Search, it can be customized with LLMs, or sorry, you can customize LLMs with it. Then it can dramatically simplify the data infrastructure, right? Like, if this vision gets realized to the extent we want to realize it, then you have a single solution. And I'm not telling you to switch to TileDB. I'm telling you to push the other databases to do the same. That's what I'm pushing you to do. I want the competition. The competition is healthy, but you need to tell the other databases to, you know, catch up and start being multimodal, do more than what they have been doing for the past 50 years, which is running SQL queries on tables. We need to do more than that. And the biggest value of all is that if it is that versatile and that flexible, as I coin it, then it is future-proof. And by the way, embeddings were not in our horizon when we started 6 years ago at all. we had the universality in mind. We wanted to satisfy life sciences, geospatial analytics. You know, we wanted to do that, but we didn't know at the time about vector embeddings. We knew about the technology, but we did not know that there is going to be a market for that stuff. But building such a thing allowed us to be able to add embeddings in a month. And this is the definition of future-proof. It didn't take us 3 years to catch up. We caught up in a month. So for the generative AI space, so that I put a little bit of context, this is a system, a platform that can combine analytics. Analytics are going nowhere. Complex data, so more than tables, embeddings, machine learning operations, and of course, the implementation of a data mesh. And I will explain how, but all in a single database solution. And we call it a DB on purpose. That's how we envision the future DBs to behave. I don't want to call it a platform, it's a database. So why arrays? So arrays shapeshift. Here, a graph can be an adjacency matrix, which is very sparse. So the white cells here mean empty. So sparsity is defined by how many empty cells you have. If the majority is empty, it's very sparse. If the majority is non-empty, you define it as dense. And there are different implementation tricks there for performance. Single cell analysis, right, different webinars. It's a sparse matrix associated with some tables. Point clouds is a three-dimensional massive empty space with points, where a point can be a cell, a non-empty cell. Population genomics, again, we can reduce it into a three-dimensional, very sparse array. Then time series or imaging or video and many, many others can be implemented as a dense array. Tables can be implemented either as dense or sparse. So in general, the array shapeshifts to match the nature of your data and to match your workloads. And it gives you massive performance boost. And it has a lot of qualities. Again, I'm not talking about embeddings here. I'm not talking about video. I'm talking about arrays, a fundamental mathematical structure, or tensor. Some people have used tensor as a term, although it's a little bit misleading. Don't use the term tensor unless you're a physicist or a mathematician. Just don't. You're going to annoy those guys. Multidimensional array, that's what it is. But we built it with a proper format in a cloud-native way, like a database, so that you can have versioning, time traveling, you have tiling and compression, you have indexing, you have metadata, you can reduce everything, even the machine learning models and files and everything into arrays, so that you have a single database based on arrays. The code base is a single thing. It's based on arrays. And then on top, we're building a lot of other value. So TileDB is a one-stop data powerhouse. And effectively, the pillars that you should remember is arrays as the fundamental data structure, a ton of interoperability. And I did see one question. We're going to talk about this in a bit. But we will never tell you to learn another language. That's insane. There are way too many out there. What we do is we offer SQL for tables, Python, R for the data science people, Go for people that are building servers, I don't know, JavaScript, and C# that those are using Windows. We have integrations with SQL engines, with distributed computing frameworks, with the entire machine learning ecosystem, but also even applications. We're very verticalized, especially now that we are at the early stages of our company. So interoperability is a huge thing for us. We're not going to tell you to learn something new. We build from scratch our whole compute infrastructure. It's completely serverless and elastic. Since day one, way before what you saw with Snowflake, Databricks, and all of that, we had already been building that stuff. But again, very small company, we're flying under the radar. So our compute, think of it as Dask delayed on steroids, because it can admit any kind of language. It's completely elastic, completely serverless. And you can build anything. You can build workflows or you can build queries, like distributed queries. And this is fundamental. It has nothing to do with SQL. It has nothing to do with arrays. It's a foundational computational framework. And finally, we go above and beyond for governance. The whole TileDB offering is enterprise grade with all the compliances, all the data, all the code, everything in TileDB is governed, access controlled, logged, like a database, because you should be doing that with all your data. It doesn't matter, even if it is files, you need to log them. You need to log the access. You need to catalog them. And we do a lot of work on those three kind of verticals, life sciences and geospatial with the sub-verticals, and machine learning for very select use cases that complement life sciences and geospatial. That's how we work. We do, of course, a lot of analytics, but right now with the current team, we have a lot of success and traction in life sciences and geospatial. So you're going to find us in those domains a little bit more than what you will see us in time series and other general analytics. And please go check our open source offerings. The first one here, the first link is the main core C++ library we have. Everything is built on top of this. And then if you go to our website under open source, you're going to see the whole ecosystem. It's a massive open source ecosystem that we're building. And then if you want to go a little bit beyond the open source and start adding, this compliance, security, governance, the catalogs, the serverless compute, and everything that has to do with visualization, then you need to be upgraded to something like our SaaS offering or the on-prem environment that we have. So you can go to cloud.tiledb.com and you can see everything there. So that's what TileDB is in a nutshell. And one more thing before we jump onto data meshes and LLMs and how everything ties in together. Please remember this. A data frame is just an array where any subset of the columns may become dimensions. Let's leave it at that for now. I'm very happy to, we have a lot of blogs and documentation around this, but for now, please understand that data frame is just a very specialized case of an array. The array is the generalization of the data frame. And therefore, I would like to make absolutely certain that we clarify confusion that I see in the market. TileDB is not yet another database. Or let me rephrase, array databases are not yet another database category. It's the expansion of the relational model. The whole relational model, everything you see in a warehouse can be readily implemented in TileDB, readily. So don't think that this is like a key value store, a NoSQL database, something else. It's all of the above in a generalized database concept. And the arrays is just the magic underneath. All right. So how do vector databases fit in here, or how TileDB fits into this whole craziness of generative AI and Vector DBs and Similarity Search and all of that stuff? Well, recap on Vector DBs. You have a bunch of raw data, images, files, genomics, anything you can imagine. And you have an application that asks similar queries. Like, for example, you have a repository of images and you have the user querying you with an image. All right, find me the similar images to this from your database. What happens is that both of those, like the repository a priori and the application on demand, go through an embedding model, a machine learning model. That's already done. It's already registered somewhere. You just query it with an API, you get back the vector. And what you get is a vector. And this is let's say that this is your query, the vector embedding, and this is your vector database. So the vector database gets predominantly only the vector embeddings of those raw data, only the vector embeddings. They're creating some kind of a 2D matrix, or that's how you should logically think about it. An array, that's an array, okay? And by the way, it's two-dimensional. They're calling each vector multidimensional. Well, a vector is one-dimensional and it has a length. It has a lot of values in there. But from a logical perspective, when you're seeing, the problem from 30,000 feet above, it's just a two-dimensional matrix, our easiest use case. And you add some indexes on top, like k-means, you can do some other stuff. Like, again, a lot of nice things here, but all in the public domain. You can build those indexes. And then this query happens fast by submitting this vector, this query vector, to the index, which goes into the two-dimensional matrix to find the actual vectors, and then it returns the results. So this is what a vector database does. So what does TileDB do? All of it. It stores the raw data. So for example, you're using a vector database for your images. Where are your images? Where are they? Where are you storing the files? Is it going to be on S3? Who governs it? Who has access? Who logs that access? After the retrieval of the images, who does post-processing? You may want to do edge detection. You may want to apply a computer vision process. Who does that? The vector database is not going to do that. The vector database is going to give you the IDs of the images that satisfy your query. And after that, you're alone. TileDB does everything. It will retrieve the actual images, going to give you the images, it gives you the framework to process the images, it governs the images, it logs all the access and so on and so forth. So everything. It also stores the machine learning model. It stores it and catalogs the actual model that you are performing this, that you are generating these vector embeddings with. Where is this model? And how do I know which model you use to generate my embeddings if you're storing the model somewhere else and the embedding somewhere else and then the raw data somewhere else? TileDB stores everything in a single platform, and I'm going to talk about data mesh later because it also combines them into data products, as it should. The raw images with the corresponding embeddings and the model that generated the embeddings need to live in an integrated data product. Otherwise, it's the Wild West. And you can even train the models.
Yeah. Stavros, we have 2 minutes left. So do you want to talk quickly about data mesh so we can then take some questions? Otherwise, some people will start dropping off.
Sure. So the most important thing, at least for today, we want to announce our own vector search capabilities, which was natural that we would do. And this is what we made public today. You can go and check it out on GitHub. And so that you understand a little bit what TileDB does, because this is very important and why it is different. So first of all, we just focused on flat and IVF flat. Those guys that work on embeddings, they understand. So it's one non-indexed approach and one indexed approach, and more are coming up. But even this IVF flat is extremely good, especially if you tweak the parameters, you're going to find amazing recall already, very, very fast. But here are the different modes you can use TileDB with, which is very different from everybody else. Number one, you can use everything in RAM like everybody else. Like you can do it in the same manner that Fies does it, as well as Pinecone, Milvus, and so on and so forth. But that's the easy thing, right? And the expensive thing, because you need very beefy machines in order to store everything in RAM. You can use out of core and out of core mode on local machine, which does not require a lot of RAM, and it's extremely fast as well. You don't need that much RAM. You can use out of core on S3. This is very important. We are probably the first ones to have rapid similarity search with vectors stored on S3. And you don't need, and everything is serverless. You don't need to manage a database at all. It's serverless. And we also have fully distributed capabilities on S3 and object stores, which give you massive scalability in queries per second and so on and so forth. And all of the above even work with batch queries. For example, you may gather 10,000 queries in a second, submit these 10,000 queries in a batch, so that, and we have a lot of sophistication there where we sort the queries and we sort the partitions and everything, so that you don't need to fetch unnecessary data twice. We did a lot of work on that respect. And just throwing a couple of numbers that we will post more details about. We're already 4 times faster than Fies, even for the simple case, which is everything in RAM, for the SIFT 1 billion data set. So we are operating today at a billion scale. We are serverless, right? You don't need to spin up 26 servers in order to handle 1 billion vectors in RAM. It's absolutely cost effective. It costs you peanuts in order to answer all those queries serverless. And most importantly, this is more than just vector search, because we're storing even the raw data. You can do analytics, you can catalog everything. It's not just yet another component that increases your infrastructure. All right, Sanjeev, I know we are a little bit over time, but I have just a couple of slides only. I suggest we take them, we present, because we are recording it. And then we can send the recording, and those folks that are dropping can absolutely go back and check. And, but I'm not, it's going to be five more minutes.
Okay.
All right. So TileDB is data mesh, right? I mean, we talked about data mesh. Okay. So what does this have to do with TileDB? Well, TileDB is a data mesh by definition. Like if you think about it, it is, because it stores all types of data in a single platform. And I do remember one of the questions, I'm going to answer it here, provides a holistic catalog. So the catalog by definition needs to be centralized, folks, right? I mean, it has to be, because how are you going to know what data another group has. There has to be some centralization for the catalog. And here's the important thing. The ownership of the data is decentralized. You are creating the data, you access control, you define the access policies to your data. It's you, nobody else. Through the platform, still you own the data. And if you don't want any other group to see it, it's not going to see it. But it does centralize the governance. How else are you going to pull this off? The access, there has to be some kind of a governance architecture to enforce the access policies on your data, but also on another team, so that it can do intercommunication between the two teams. Otherwise, it's going to be impossible. Everybody's going to be implementing a different governance infrastructure. So it's going to add a lot of complexity to the organization. Build those things once. And it provides a very common and well-defined compute infrastructure and APIs, which is a prerequisite for the data mesh. And it allows the definition, documentation of data products with something we very simply call groups. It's just like a hierarchical structure, very, very much like folders. The difference is that the folders are self-contained. They can be shared as integrally. They can be access controlled, individually. But at the same time, we don't do any movement of data, especially on object stores, because it's extremely expensive. And also, one data asset, which might be a data set of 100 terabytes, may belong into two data products. What do you do in that case? So what we do is that we virtually define the ownership of those assets in the groups. You don't have to do it in a physical manner. The physical manner is opaque to you. And particularly for generative AI, as I mentioned, you can store the raw data, the embeddings, the machine learning model, the code, a description, a documentation, everything in a single place, which is massive. Like, imagine how many tools effectively you're replacing if you don't have something like this. Or sorry, if you have something like this. So imagine how many tools you need to combine yourselves to build this infrastructure if you don't have something like that. All right, very quickly, how did we build it? There are 2 more slides and we're finishing. So that you know how such a thing can be built, all right? Because we had a lot of resistance in the early years by everybody that this is kind of impossible to build. So I'll tell you how we built it, and I believe this is the rigorous approach to take. There's no anything else is gonna crumble. You start at the bottom with something like an open source format and engine and data spec. If the data is not open source, nobody's gonna adopt it. Like, it has to be open spec. And we chose very carefully the fundamental data structure. If you start adding Parquet and ZAR and ORC and another 1,000 formats, there's going to be yet another format that you need to include in your infrastructure. We consolidated everything into a single powerful format and storage engine on arrays. That was number 1. Plus all the wrappers. We have 10 APIs fully maintained by us and 20 integrations with tools and pretty much everything else that exists out there. So that took a long time to build properly. The second thing is that we needed to build something which adds the governance aspects, like the catalog and access policies, some more secrets, some more syntactic sugar for vertical assets, like if something is for genomics, if something is for geospatial, and of course the compute platform. The compute platform needed to be part of the database, because there you have access policies too. For the code you're running, even the code needs to be access controlled and logged. And now we're at this stage, number 3, because number 1, number 2 we've done. And this is where we're starting to build automation. This is where you will start seeing more fancy UIs from us and automation and one-click ingestions and all of that. But without the bottom assets, it would have been impossible for us to pull this off. And the holy grail of data is to customize LLMs. But you see, we consider this as the last step. We see a lot of organizations jumping on customized LLMs today without having figured out how to manage their data to begin with. So my advice, start with the data management. Customized LLMs will come later. All right, conclusion. Generative AI has massive promise, excellent technology. There is a lot of hype, but what we all need to do is to be a little bit careful. Like whenever we're jumping onto this shiny tech too fast, it creates this hype, it creates panic, like people want to adopt it because they feel they're going to be left behind. And that creates a lot of confusion. So yes, investigate, try to adopt it, but do it in a principled manner. And learn how to see through the hype. Like, we've done it multiple times already, and it's as if we're not learning. We're not learning anything. We're behaving the exact same way in every hype. So number one, ask a lot of questions to vendors. Somebody's selling you a customized LLM, like scrutinize them. A lot of questions. How are they different from the competition and everything? Ignore funding rounds and valuations. This just confuses you. Like, there are so many things that go into financing rounds that may have nothing to do with the technology. Scrutinize business analysts and marketeers. Ask Sanjeev. Sanjeev is excellent. So go to him and ask him a lot of questions. He knows. But also, try to see through a little bit of crazy marketing and all of that stuff, right? Like, create a dialogue, a very healthy dialogue with them, and they're going to answer. Especially Sanjeev has been excellent when we were interacting before this webinar. And what better way to do it than just do your own deep research? Don't take anything for granted. Even this webinar, I told you a lot of things. Go back, research, see if everything checks out. And try to create relationships with the real experts. And please trust me, the real experts are those building the systems. There aren't too many, but you engage with them. I will introduce you to some people. We can answer questions, but be very close to people that know how to architect and build database systems that take decades, not a month, a decade to build. And regarding TileDB, it's a powerful tech. We do everything we promise. We bring together analytics, complex data, customized LLMs. However, caution, this is a paradigm shift. We're telling you pretty much the opposite of what everybody else is telling you with regards to, how many technologies you need to adopt and everything. We're trying to consolidate technologies, and others are trying to fragment the technologies or fragment your infrastructure by selling you many technologies. So you need to be good. You need to be okay with this cultural shift that we are proposing. And second, it's not yet another database. It envisions to redefine and expand the concept of the DB as we know it. We don't want to build yet another database. That's not our intention. And that's why this is very, very difficult to build. And that's why we're so proud to have this amazing team, this amazing product that we've built over many, many years. So thank you. Apologies for abusing a little bit of your time. I still see several people on, which is awesome. I'm very ready for questions.
Yeah, let's go to the questions. We have a lot of questions that have come up, some excellent ones from Dan Everett. The first question he asked is, how do you balance the need to have autonomy and interoperability? And this question came up when we were talking about data mesh that time. So let me answer this because there's a TileDB angle. Stavros, feel free to jump in. So the pendulum keeps shifting between should we do centralized, decentralized, and we go back and forth for decades. The right answer, in my opinion, it's a hybrid. We just cannot have one or the other. There's no silver bullet. So what I mean by that is you want autonomy and you want interoperability. Autonomy comes by doing decentralized data applications. Interoperability comes by doing a centralized data infrastructure. Although data mesh says self-service data infrastructure, every team should have its own choice, but every successful data mesh I have seen, they'll pick a common, let's say it's Snowflake or Redshift. Same thing, it could be TileDB. So with TileDB being the common platform, you get the interoperability, and then every domain does its own development.
So this is an excellent question. So I'll tell you how we approach the problem. I mean, as Sanjeev said in the past, like a lot of people have their own implementations of data mesh, and it's absolutely fine. Here's one problem you may encounter if every team acts completely independently. Suppose one team is doing oncology, another team is doing genomics. And oftentimes you need data from both, like the scientists need to fuse data. Suppose oncology chooses one database and genomics chooses another database. And now the CIO of the company or anybody else, let's say the CIO, but because the CIO sees everything, wants to see with a simple search what data sets pertain to a particular hospital's data for a particular patient for oncology and for genomics. Before data mesh, you had to call the IT department of oncology, run this query on your database because I'm the CIO, I don't have direct access to the database. And then I would have to go to the genomics department at IT, call, hey, give me this. And then they give me back the data and I don't know what, like I'm gonna call a data scientist or data engineer to fuse and give me the insights. Now, this is what they do if they have completely separate infrastructures. Now, to solve this, some solutions came up with centralized governance and catalogs, which are a layer on top. So already you had this disconnected IT infrastructure, two different IT teams. Now you're putting another one, and those guys are going to fight. Who's going to handle this? Another company on top, just catalog. It catalogs only the assets, doesn't do anything else. And another one only for governance, for access policies. So still they're centralizing it, because otherwise, how am I going to, then it's not a data mesh, it's silos. The other thing is I need to go and ask a question to the silo. If it's not silos, there has to be a centralized portal, a data mesh, or not many data meshes. So what we're saying is, you don't need one database, second database, catalog, access policies. You don't need four. You need one. A database who is multimodal to capture imaging, a database who is multimodal to capture genomics and tables, phenotypes. And that database comes with a catalog and it comes with governance. And now each one of the teams, the two teams, can define their own data, store it in TileDB, and say, only I can see it. Not even the CIO, only I can see it. Great. Then the other team says, only I can see it. And then they can select, and the TileDB platform obeys what you're saying, because it obeys the access policies and the catalogs and everything. And still, you get the interoperability with the data, because for the imaging data, the TileDB, for example, gives you an image viewer and the API of the oncology people. It's part of the database. It's not SQL. It obeys the API. It's multimodal. It has the API built in. And the same thing for genomics. It has the APIs that the genomics people use. It's built in. So it is interoperable by definition. That's how we solve this problem.
Very nice. How do we are 15 minutes over? Let's
continue.
Okay.
Let's go through the questions.
Okay. So there was a question, the next question I saw, which is also in the data mesh, was sounds like it's a people-centric approach and not an architectural decision of technology platform setup. That is, so Ananya Som asked that question, absolutely correct. That's what data mesh is. What Stavros is showing is the next level of making that data mesh actionable through the TileDB, which he just explained. So with that, let's go to the few open questions. The first question is, would you call a fine-tuned LLM a data product? That's an interesting question.
I think it could be a data product on its own, or the fine-tuned, in my opinion, the way I would do it, again, the data products depend on the experts, right? They do. That's why they say in the data mesh, there is a domain expert who has, who defines the data product. The way I would do it would be, I would store the LLM itself or a reference. It could be just a link to OpenAI or whatever it is. But also I would store references to the data I used to fine-tune. Isn't this part of the fine-tuned LLM? Should I not know what this LLM was fine-tuned on, so that if there are updates, I can continue the fine-tuning to include the updates? So the data used to fine-tune the LLM should be part of the fine-tuned, part of the data product. So yeah, either standalone, but in my opinion, also the data used to fine-tune the LLM should be part of the data product.
Very nice. So moving on, next question also from Dan is, what are your thoughts on retrieval-augmented LLMs, which use an external knowledge graph to augment the capabilities of an LLM?
Excellent. So for those that don't know, and by the way, I don't want to position myself as a machine learning expert in anything. We learn as we go because this is a very dynamic domain. Don't think that we know all the answers, but for those that don't know, retrieval-augmented generation, RAG, is exactly what I mentioned. The customized LLMs, that's what it is, RAG. All right, that's another way to call them. So, but the question here is a little bit different because there is a trend there. They're saying, instead of giving tools to connect to 1,000 databases with very difficult queries that may have to be run on demand online, what if from my databases, I could, in an offline session, I create a knowledge graph based on domain expertise. Now I have my knowledge graph, and instead of giving access to those individual databases, I give as input to the LLMs the knowledge graph. Absolutely valid. The difficulty is in producing it. It's not as trivial, especially for genomics and geospatial and the battlefield situations for defense. Like, this is not trivial to build a knowledge graph. If you have it, excellent, but still you need to maintain it with updates and all of that stuff. And make no mistake, you still need the databases and the whole stack for the raw data that created the knowledge graph. So again, you're adding yet another layer of complexity, which is fine. Please remember, you need that. You need the databases with the images, with the battlefield information, with the cancer information, with the drug information. And on top of this, like, depending on the vertical, you build knowledge graphs. But absolutely valid. Yes, this is what the RAG LLMs are doing.
That is great. So we have a question from Prashant. He's asking, Microsoft released a new feature on Azure to train LLMs to create org-specific chatbots. What are your thoughts on the simplicity that model offers?
Yeah, excellent. This is one of the easier, well, take this with a grain of salt. It really depends on what they're doing, because if it is a chatbot on support, this is something today we were discussing internally about building a chatbot for our own documentation. Well, if you are to train a model only on my documentation, that's easy. That's not going to take, it may take a day, couple of bucks to build by an expert, right? That's fine. So I need to understand, is this chatbot going to work on my data, which is at the time of this webinar, petabytes of data? That's going to be expensive. So it really depends on what they're doing. Excellent usability goes without saying. I really believe that every single organization eventually is going to have some kind of a version of an LLM for chatbots, which is the obvious use case. Chatbot for support. But this is yet another use case of what we're explaining here. It's not different. Just take everything that those guys are saying with a grain of salt. Ask more questions. How many data are you training this on? How much is it going to cost? What types of questions is it going to answer? That's, back to my conclusion in reading through the hype.
So the last question is, will there be a need for graph database along with TileDB? And after that, we'll wrap it up.
So listen, a graph, and I showed this in a figure, a graph is, in our world, an adjacency matrix. It's a two-dimensional array, nodes by the same nodes, and there is a non-empty cell when there is an edge at the corresponding cells. Okay, the corresponding nodes, sorry. And this is a sparse matrix, and we can handle it perfectly. And because of our two things, like first, the infrastructure we have, and second, the expertise we have internally in the team, we have some graph algorithm experts. We can build any graph algorithm using just TileDB. Now, why is it not there yet? We didn't have any aggressive customer coming in saying, I want it, or they were good enough with some open source tools and whatnot. But yes, I mean, in our vision, every single specialized database should be part of TileDB, or a specialized database functionality should be part of TileDB. It's just a matter of time. Fundamentally, we can support. Now, do we have all the automation, the query language, integrate with Cypher and whatnot? No, we need a little bit more justification from the community, from the users, from the customers, in order to just build this layer on top. But nothing prevents us from doing this.
Excellent. Thank you so much, Stavros. This was fantastic. This is one of the most in-depth exploration we've done on this topic. So I really want to appreciate all the time, all the questions that everyone has. We still have dozens of people who stayed on till the very end. Thank you to all of you
We appreciate
for
you.
staying for almost 1.5 hours and going through this. Always open to questions. Please connect on LinkedIn if you would like. And looking forward to come to New York Unconference, which is on this week, Thursday at Javits Center. It's in my LinkedIn profile. Thank you so much, everyone. Take care.
Thank you all.
Thanks.
Bye.